Hello and welcome to the Math 171 online course final exam review session here. A session specifically designed to help you know what to expect for what's coming up on the final exam for our course, various particulars about it, and also some general announcements here as we're almost to the very end of the course. So I want to cover two or three different things here, several different things before we actually get into the specifics of what to expect on the final itself. First of all, let me remind many of you that you must make your appointment to take the final exam really immediately. Immediately go by and make your appointment if you haven't already. Approximately half of you have already and approximately half have not as of this afternoon, Monday, December 7th. And congratulations, those of you who already have. That's very excellent. And the rest of you, please get over as quick as you can. The slots are filling up. There's certain times already that are not available at all. For instance, I think Thursday evening is not available any longer. Much of the day Friday is not available, and next Tuesday evening is not available, as I understand now. So as quick as you can, get your appointment made and try to get a time slot that works well for you. So that's the first point here. We have to sign up to take the final, of course, before you can actually take it. A few other pointers here. We are presently on Monday, December 7th, and that means you have your fourth and final lab activity due tonight. The Chapter 4 lab is due this evening at 11:59. Many of you have already submitted that. That's great, and I trust many of you are working on it. Well, that is due this evening, and if with all the pressure at the end of the semester you can't make it in till tomorrow, tomorrow will be available with just 10 points off the grade. So if you get in by Tuesday evening, the same time, of course, that your online WebAssign Chapter 4 test is due. But anyway, if you get that in by tomorrow evening, it's only 10 points off the grade. So just one day late. And I'll mention this too. I have decided to do something right here at the end I wasn't actually planning on doing, but I'm going to do this maybe one time here anyway. From now until next Monday evening, December 14th, 11:59 p.m., 1 week from tonight, I'm giving you a grace extension period to turn in any lab activities from earlier this semester that for any reason you didn't turn in. If you turned in, say, labs 1 and 2 and didn't turn in 3, or you turned in 2 and 3 and didn't turn in 1, any of those 3 previous labs you never turned in, you can turn in now with only a 20-point penalty off on the grade. So if you turn it in and scored 90 on the paper, then you earn a 70, 20 points off. But that's a whole lot better than a 0. So I'm offering this for whatever reason. There's a number of students who didn't get a lab or 2 in. And so if you get those in between now and next Monday evening, you can get a good portion of your credit still. And that'll work for the Chapter 4 lab. If you don't get the Chapter 4 lab in by tomorrow, you can still turn it in until next Monday also with 20 points off. Okay, so that's the lab activities. And I mentioned this in passing. The final online chapter test in WebAssign is due tomorrow evening, Tuesday, December 8th. So the Chapter 4 test online in WebAssign, as the previous 3 tests were, is due by tomorrow evening, December 8th. And also, your first 2 lab papers are now available. The first one's been up for a while. The second one is now available to you. The graded lab papers with my notes and feedback on them are available to you in Moodle. You can go back to where you submitted your lab paper and review it now. It's posted back up with the grades on it. for both the first lab and the Chapter 2 lab. The Chapter 3 lab has been graded. The grades are in WebAssign, and they will be in Moodle also, with your graded papers uploaded back into Moodle, again, where you yourself submitted it previously. And you should be able to access that by sometime later this evening, or at least by tomorrow. At least by tomorrow, let's be safe on that. The Chapter 3 labs will also be posted back up into Moodle, graded with feedback. So you'll have the first 3 there. And those could be useful also in studying for the final exam, those lab papers. The midterm exams, I've decided I am going to return those to you also with your graded feedback notes on each person's paper. And since you did not submit those through Moodle, it's not really easy for me to post them up in Moodle for you. So what I'm going to do is attach each student's paper to an email and send it to you by sometime tomorrow. So if that's useful to you too, you'll have your midterm exam back with the notes and feedback on your graded paper. And the Chapter 4 labs, of course, are coming in mostly by tonight. With the huge volume of papers coming in this week, I cannot promise a date that I will have those graded. They will be graded, but I cannot exactly promise when. If it's sooner rather than later, I'll send you an email and let you know, but otherwise I'm going to get them as soon as I can. And I also plan, just to let you know, to post up the answer keys for all 4 labs. Chapter 1, Chapter 2, Chapter 3, and Chapter 4, to put up the answer keys for all 4 labs into Moodle. And those could be helpful to you all for studying purposes for the finals. So I'm going to post those up by sometime tomorrow also. So lots of points to go over here of different assignments and activities. So now let's get into talking about the actual final exam itself. Once again, you will be allowed 2 hours in the Academic Success Center to take the exam. I have not heard from anybody that you wish to take it anywhere else. Today is the deadline to let me know if you want to take it somewhere else other than the Academic Success Center here at Western Piedmont. If you want to take it anywhere else, you need to let me know before this day ends. So far, nobody has, and I'm pretty much believing everybody's going to plan to take it here. And of course, it's proctored, as was the midterm exam. It's proctored, and you're allowed a total of 2 hours to take the exam. It is timed, and it is proctored. You're not allowed to use your textbook or any notes, but you will be allowed to use the computers to access a graphing facility only. Of course, you're allowed to bring your graphing calculator, any kind of calculator. Graphing calculator is you're definitely going to want. For those who like to use Desmos on the computer, you will be allowed to do that. You will be allowed to really use any graphing facility on the computer that you wish. Desmos is probably the most popular one, but you are allowed to use computers. So that is included as part of the accessories for taking the final, having the availability of a computer right there in the Academic Success Center. So you can expect to see questions from all 4 of the chapters that we've covered in the book. Questions from Chapter 1, Chapter 2, Chapter 3, Chapter 4, and 1 question from out of those 3 sections in Chapter 8. There's going to be a total of 10 questions plus an extra credit question. And let me remind you too, this final exam, this is really a significant test you're taking, not because the test itself is weighted more heavily than any other test you've taken already. It's weighted the same as the midterm was, that is, it's 20% of your overall grade, just like the midterm exam was. But the significance of this is that the final exam can, the grade, as long as it's higher than at least one of your previous online WebAssign chapter tests, will replace that previous lower grade earned on some one of the 4 online WebAssign chapter tests. So for instance, you did fine on 3 of the online chapter tests, but one of them you were just having a bad day and you only made a 63. But then on the final exam here, you made an 84. Well, that 84 will go back and replace the 63 as the grade for that previous online chapter test. The 63 is totally gone and replaced with the final exam grade of 84 since it's higher. And then the final exam grade of 84 also stands as 20% of your grade as the final exam grade also. So that's how the system works. And let's start talking about some specific types of problems that I would want you to be prepared for, the kinds of things that I think are just some of the most important material out of each chapter. For instance, in chapter 1, we talked about functions, very basic definition of a function, and you should be able, if I give you a function, you should be able to, first of all, on paper, sketch a graph of the function. And so what I suspect most everyone's going to do is use your graphing calculator or graphing utility, Desmos, whatever, and get a view of the graph of this function and then transpose that graph from your graphing utility, draw a set of axes on the paper, and actually draw the graph. And make sure when you sketch any graphs on the test that you do show your scales, your X scale, 1, 2, 3, 4, 5, your Y scale, 2, 4, 6, 8, 10, whatever it is, show the scale. And make sure your graph is understandable and legible. Secondly, you should be able to tell what is the domain and what is the range of any function that's provided to you. Remembering that the domain is the set of all x values of the function, the range is the set of all y values of the function. I am not as particular as WebAssign on how you express your domain and range. For instance, you can express the domain by saying all real numbers except 2 and 5, for instance, or you could say you could use intervals. If it was all real numbers except 2 and 5, you could use 3 intervals. The interval from -infinity to 2 with rounded parentheses, then a union symbol that looks like a capital U, and your second interval 2, 5 in parentheses, and the third interval 5, infinity parentheses with a U in between the second and third intervals also. So you could do it with interval notation, or you could do it with words, or you could even use inequalities. You could say, for instance, x is less than 2, or 2 is less than x is less than 5, or 5 is less than, or x is greater than 5. With 3 inequalities that way, you could also express the domain. So there's lots of different ways you could say it, and as long as it's correct, it's acceptable. You should be able to identify any x-intercepts or any y-intercepts of any function. If it's actually a true function, of course, there can be only one y-intercept, if any. There can only be one, or else it's not a function. It would violate the vertical line test. So there may be a y-intercept or there may not. I'm actually not going to count off if all you do is give me the numbers. If you say the x-intercept is 5 and the y-intercept is -3, I'll know what you mean for intercepts. It's better, it's preferable to put the point notation. For instance, if the x-intercept is 5, it's best to put parentheses. You start with a parentheses 5, 0 and close a parentheses. And for the y-intercept of -3, to say parentheses 0, -3, close a parentheses. That's better, but I will accept if you just give me the numbers for intercepts. But I have to take off points if I ask you to tell, for instance, what are the vertical asymptotes or the horizontal asymptotes, and all you do is give me a number. Because asymptotes are not numbers, they are lines. So for instance, every vertical asymptote should be x equals some number. Every horizontal asymptote should be expressed as y equals some number. And you should be able to tell, using interval notation, to describe where any particular function is increasing or decreasing. For instance, the simplest, most basic parabola, y equals x squared, with its vertex right at 0, 0. It's coming down forever from the left, down to the origin at 0, 0, and then it goes up to the right forever and ever and ever, off to the right. And so you could say it was increasing, say it was decreasing on the interval parentheses -infinity, 0, close the parentheses. So on the interval from -infinity to 0, it's decreasing, and then on the interval from 0 to +infinity, it's increasing. So you put parentheses 0, infinity, and close the rounded parentheses. That would be the interval for where y equals x squared is increasing. Also in chapter 1, we did operations with functions like adding, subtracting, multiplying, and dividing two functions. And so you should expect me to give you a couple different functions, say maybe f of x equals something or other, g of x equals something or other, and you should be able to find how much f plus g of x is, f minus g of x, f times g of x, f divided by g of x, and those are pretty much arithmetic algebra type operations, pretty straightforward. You just add the two, subtract one from the other, multiply the two expressions, or divide one expression into the other. And if you have to divide, remember, if one of or both of them are quadratics, you want to factor them both to see if any parentheses cancel out top and bottom. So present your answer in the most simplified manner after you cancel out. And after we studied that, if you recall, we did composition of functions. So this is where you take one function composed with another. And this is the notation where you say f and the little circle g in parentheses of x, x in parentheses 2, or g, the little circle, f in parentheses of x. So you can have f of g of x, or you can have g of f of x, and they're not the same. This is not like adding or multiplying functions. This is actually taking a function of another function. And remember, when you do that, if it's f of g of x, for instance, then you insert the g of x expression into the f of parentheses. So you'd have f of something, something, something in x, close the parentheses. And then with your f of x function expression, everywhere there's an x in that expression, you would now insert the entire g of x function in for x. Everywhere there's an x in f of x. And then you would expand that out and do all the algebra, simplify it down, and that would be your answer to how much is f of g of x. As a reminder, f of g of x and g of f of x are generally very different. for two functions, f of x and g of x, but they are only the same if and only if f and g are inverse functions. So if they're inverse functions, then f of g of x does equal g of f of x. And if f of g of x happens to equal g of f of x, then you also know conversely that yes, the two functions are inverse functions. Okay, on to what you can expect to see from chapter 2. Be prepared to solve any kind of quadratic equation you might be given. I'm going to suggest there's 3 fundamental types based on their complexity. There's the nice simple type that you can just look at and factor into 2 parentheses and set each parentheses equal to 0 and get your 2 answers. Check your 2 answers, make sure they're good, and you're done. I would say we would all agree that's the easiest kind. Then the other 2 kinds are where you have to use the quadratic formula. And at this point, let me mention something else that you can expect when you come to take your final. You will not only be given the final exam itself, you will be given a handout to accompany your taking the final. And this handout will be basically what you received. Well, no, I'm sorry. You did receive a handout with the midterm, but you will receive what you received with the midterm, since the final exam is cumulative all the way back to the beginning of the semester, but you will also receive some additional handout materials for Chapter 3 and Chapter 4, and if necessary, even for the section in Chapter 8. So you will receive handout material to accompany the final exam from Chapters 1, 2, 3, and 4, and possibly even something out of Chapter 8 if necessary. So, yes, I definitely wanted you to know about that. Okay, continuing on with discussing solving quadratic equations, the quadratic formula can output 2 different kinds of answers to you, basically. If it's a more complicated problem, the 2 types of answers you could get are either real numbers that have square roots as part of the answer, or complex numbers that have I as part of the answer. So for instance, the easiest kind, again, you just factor it and you get your 2 values for x. The second and third kinds, you use the quadratic formula, and on the second kind, you'll end up with an answer that has a square root in it, often over a denominator. It might be like, for instance, 3 plus or minus the square root of 5 all over 7, for instance, or 2 plus or minus the square root of 2 over 3, something like that. Those are real numbers, but it has a square root in it. Or you may get where there's no real solutions, just 2 complex solutions. For instance, the answer could be something like 2 plus or minus the square root of 3 times I over 2, or 7 plus or minus 3I over 4. So lots of possibilities, but fundamentally it's going to come down to either you could solve it by factoring, or you can solve it using the quadratic formula. And remember, your answers may be real numbers or they may be complex numbers. If your square root turns out to be the square root of a negative number, do not stop there. Don't leave it as the square root of a negative number, but change it over to the I notation. So for instance, if your answer was 2 plus or minus the square root of negative 5, don't leave it like that. You would pull the minus out as an I, the minus being a negative 1. The square root of negative 1 is plus or minus I. So if you had 2 plus or minus the square root of negative 5, your final answer would be 2 plus or minus the square root of 5 times I. And of course, I outside the square root. And many of you prefer to put the I in front of the square root, and that's perfectly fine. You can say 2 plus or minus I times square root of 5. Also be prepared from chapter 2 to solve an equation with a square root expression. I will mention one here. Again, the iPad facility is not working, unfortunately, so I'm speaking with you at least. But if you had an equation like I'm about to say, 2x minus the square root of 4x minus 3 equals 3. And I'm going to see if I can do something here. If I can use the here we go. I'm going to use the equation facility here in Microsoft Word to type this equation in. So it's 2x equals the square root of 4x minus 3 no, sorry. I wanted 2x minus, not equals. There we go. Equals 3. So that's our equation. 2x minus the square root of 4x minus 3 equals 3. And if you recall, to solve an equation like this for x, we're going to square both sides of the equation, such as that, and then we're going to get a quadratic, and we're going to apparently get two solutions for x. But if you recall, you go through all these steps of algebra, and you apparently get typically two different answers for x. You may recall that oftentimes one or even both of those answers may be no good. They may be what you call extraneous solutions. They do pop out from doing the algebra, even doing the algebra correctly. They appear to be a solution, but when you were to go back and plug them into this original equation given here for x, it does not work. It will not make a true equation. For instance, this one right here, what we would want to do is subtract 3 from both sides and add the square root to both sides, so that we would come out with, then we would, let's get this going again here, we would come out with 2x minus 3 equals the square root of 4x minus 3. And then we would square both sides. We'd square the 2x minus 3 in parentheses, and you'd have to FOIL that out then. 2x minus 3 times 2x minus 3. It is not just the little term 2x squared and the term 3 squared. No. Most common mistake, and that's still a mistake. It's 2x minus 3 times 2x minus 3, which is going to come out to be 4x squared minus 2 times 6x, so minus 12x plus 9 on the left. And when you square the square root on the right, that's nice. It just becomes equal to 4x minus 3. And then you do some algebra and get all the terms on one side of the equation. It turns into a quadratic. It'll actually turn into 4x squared minus 16x plus 12 equals 0. Divide everything by 4. X squared minus 4x plus 3 equals 0. Factor that into x minus 3 times x minus 1 equals 0. So it would appear that x equals 3 or x equals 1. But here's where you do not stop and go on to the next problem. You got your two supposed answers, x equals 3, x equals 1. When you go back to the original equation given up here, plug in 3 for x and plug in 1 for x, you get two different outcomes. If you plug in 3 for x, it becomes 2 times 3 is 6, minus the square root of 4 3's minus 3. That's 12 minus 3 is 9, square root's 3, so 6 minus 3 equals 3. Perfect. Check. X equals 3 is a good solution, what we call a valid solution. But let's try the 1. First of all, if you put the 1 in the square root, 4 times 1 is 4. 4 take away 3 is 1. Square root of 1 is 1. So far, so good. But when you plug in 1 for x into the 2x term, 2 times 1 is 2, and here's the problem. 2 minus the 1 we got for this square root, 2 minus 1 is not 3. 2 minus 1 is 1, and 1's not equal to 3. So x equals 1 is what we call an extraneous solution. It is not a valid solution. This problem, if you were given a problem, if you were given this problem right here, there would be only one answer, x equals 3. Okay, what kind of problems can you expect from Chapter 3? Chapter 3 is where we talked about polynomial functions and finding their zeros. So finding their rational zeros, finding their real zeros, and finding their complex zeros. We use the rational zero test to help us in this. We use Descartes' rule of signs. We use synthetic division. We did lots of different things to determine whether something is a zero or not. And you can expect to be given one. For instance, let me type out one here using the equation function again. So let me type one out. Whoops. Yeah, here we go. F of x equals no, that's not. Let's use this. Okay. Minus 16x plus 12. There we go. Okay, f of x equals 6x to the fourth plus 25x to the third minus 69x squared minus 16x plus 12. Now these kind of problems take a while. First thing you want to do is use the rational zero test to list out all the possible rational zeros. And here's where you do that P over Q analysis, where P is a factor of the constant here at the end, some factor of 12. And here's, remember, if you remember, use all the plus or minus signs. So the factors of 12 are 1, 2, 3, 4, 6, and 12. And you do plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Those are your possible numerator terms. Then the denominator terms, what we call Q, are the factors plus or minus of the leading coefficient, the 6 coefficient on the term of highest degree, in this case on the x to the fourth term. And the factors of 6, of course, are 1, 2, 3, and 6, so that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And they go on the bottom. So what you have then is those 6 different numbers with plus or minus signs in the numerator, which actually represents 12 different numbers. And the 4 different numbers, 1, 2, 3, 6, with the plus or minus signs, are actually 8 numbers in the denominator. And then you have to put all those together and eliminate duplication and list out. I will expect you actually like you did on the Chapter 3 lab, actually list out all the possible rational zeros, all the possible P over Q combinations. And let's try to do that using our equation function for this particular problem. Again, P can equal, let's get the, yeah, here it is, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, or plus or minus 12. And Q can equal, I'll do it down here, Q can equal plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. I don't know why that did that. There we go. And then we can put those together so that P over Q can equal any of these terms up on the top divided by any of these on the bottom. So first of all, the plus or minus 1, 2, 3, 4, 6, or 12 all over plus or minus 1, it just gives you those 12 whole numbers. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And now we have to put all these plus or minus 1, 2, 3, 4, 6, and 12 over plus or minus 2. And then we're going to do them all over plus or minus 3, and finally all those over plus or minus 6. But it's going to repeat some here. For instance, plus or minus 1 over plus or minus 2 is just plus or minus a half. We have not done that yet, so let's do that. Plus or minus 1/2 and then plus or minus 2 over plus or minus 2 is actually just plus or minus 1, and we've already done that, so that's a duplication. We don't write that again. Then plus or minus 3 over plus or minus 2, that's new. So it's plus or minus 3/2. And then plus or minus 4 over 2 is actually just plus or minus 2, and we've already got that way back over here. Plus or minus 6 over 2 is just plus or minus 3, got that. Plus or minus 12 over plus or minus 2 is just plus or minus 6, got that. So, on to plus or minus 3 in the denominator. Plus or minus 1 over plus or minus 3, now that's new, we don't have that. Plus or minus 1/3. Then plus or minus 2 over plus or minus 3, hey, that's new too, plus or minus 2/3. Don't have that one. Plus or minus fraction, whoa, yeah. And plus or minus 3 over plus or minus 3 is plus or minus 1, we got that way back here. Plus or minus 4 over plus or minus 3, that's a new one. Let's get that. Plus or minus 6 over plus or minus 3 is just plus or minus 2. We got that already. And plus or minus 12 over plus or minus 3 is plus or minus 4. Got that too. All right. Down to the plus or minus 6 in the denominator. Plus or minus 1 over plus or minus 6. That's a new one. That is plus or minus 1/6. And then plus or minus 2 over plus or minus 6 is 1/3. We've already got that. Plus or minus 3 over plus or minus 6 is 1/2. We got that. Plus or minus 4 over plus or minus 6 is 2/3. We got that. Plus or minus 6 over plus or minus 6 is plus or minus 1. We got that. Plus or minus 12 over plus or minus 6, plus or minus 2. We got that too. So we are done with our list. There we go. Let's count how many numbers are in our list. So P over Q, these are the possible rational zeros. Let me put this right here. These are all the possible rational zeros. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, each with a plus or minus, and I see I forgot to put one in there. So let's put a plus or minus in front of that 1/6. There we go. So there's 12 different numbers, each with a plus or minus in front of them. So 12 times 2 is actually 24. And I'm going to put a little note of that right up here. There are 24 possible rational zeros. And then you could use either synthetic division or plug those numbers into the given function for x, and you're going to find out some of those numbers actually work. If you do the synthetic division, you end up with a remainder of 0, which means that that number is a 0 of the function. Or if you plug that number, any of those 24 numbers in for x into the given fourth degree polynomial up here, and it comes out the polynomial is equal to 0, then you've got a 0. But the easiest way that I trust you all know is just to graph the thing. If you graph this big, huge polynomial given to us right up here, and you observe where that graph crosses the x-axis, this is especially easy in Desmos. If you graph one of these things in these polynomial functions in Desmos and you look and see where it crosses the x-axis, those are the zeros. And so you get your values for your actual zeros that way. And you'll, for instance, you'll find that this one right here crosses the x-axis 4 times. And so it is true that the 4 actual zeros of this function are 4 of those 24. They are exactly -6, -1/2, 1/3, and 2. Those are the 4 actual zeros. And let's consider other possibilities. That sort of settles this one. But what if you only had it cross the x-axis 2 times? Then probably you'd have 2 real zeros, and hopefully rational ones out of this list. And very likely the other 2 zeros are complex zeros. And how could you find those? Well, one way you could do it is to turn, if you know, say, 2 of the zeros, you turn those zeros into factors and multiply them together. If you knew, for instance, that -6 and 2 were the 2 zeros, that's where it crossed the x-axis. Then you do x minus -6, which is x plus 6, and x minus 2, and multiply those together. And you get a quadratic. X minus 6 times x plus 2 would be x squared minus 4x minus 12. And then you would do a polynomial long division and divide that into this big long x to the fourth polynomial, and you'd dividing that quadratic into this, you'd end up with a quadratic. And since you use two of the factors of it, two of the zeros of it to make the two factors, there will be no remainder. It will come out perfect as a quadratic. And then you just have to solve that reduced quadratic for its two zeros, probably using the quadratic formula. And even if they're complex zeros with I, it doesn't matter. Or if there's square roots, it doesn't matter. Because you've got it down to a quadratic, use quadratic formula, you can find the zeros, and that way you can find all the zeros. Here's another helpful hint. If you're given a big long polynomial like this and asked to find all the zeros, and you are told that one of the zeros is a particular it's a particular complex number, like 2 minus I, then you instantly know something. If you're given that 2 minus I is a 0, remember, anytime with these rational functions, these polynomial functions like this, polynomial functions, if you know one of the complex zeros, you know the second complex zero, because complex zeros always come in pairs, the conjugate of each other. So if 2 minus I is a 0, its conjugate 2 plus I is a 0. If they tell you that the complex number 3 plus 4i is a 0, then its conjugate 3 minus 4i is a 0. For the conjugate, all you do is change the sign in front of I. And then once you know those two complex zeros, if that's all you know, then you can make those into factors, x minus one of the complex zeros and x minus the second complex zero. And then you have two parentheses you can multiply together. Each of the parentheses will have two terms. Like if it was 2 minus I and 2 plus I, you'd have x plus 2 minus I and x plus 2 plus I. Multiply those together and you'd get a nice quadratic with no i's, just a real number quadratic. And then you could divide that quadratic into the cubic or fourth degree function you were given, trying to find all the zeros of, and reduce it down. And once you do the polynomial long division and divide that quadratic made up of the product of those two complex factors, then you get either just a linear or a quadratic expression, and you set that equal to 0 and solve for the one or two zeros there, and then you're finished. Also in chapter 3, please remember how to find, if you're given a rational function, remember how to find horizontal asymptotes, vertical asymptotes, slant asymptotes, or holes in the graph. And remember, if you're given something like with a quadratic divided by a quadratic, you factor the top, factor the bottom, cancel out anything you can, any parentheses you can. And if you cancel out a parentheses top and bottom, that parentheses is going to tell you where there's a hole. For instance, if you cancel out x minus 7 top and bottom, then x minus 7 makes x minus 7 equal to 0, so there's going to be a hole at x equals 7. But if there's a parentheses on the bottom you did not cancel out, say x plus 4, that means at minus 4, at x equals negative 4, you've got a vertical asymptote. Vertical asymptotes occur where they don't cancel out top and bottom. Holes occur where they do cancel out top and bottom. And you're also going to be given a word problem. And this is a problem that you're going to have to work it out yourself and come up with an equation, which is going to be an x to the third equation, a volume equation, a way of expressing the volume of a box that you're going to cut out of some cardboard as it's going to be described to you. And you have to figure the length of it and the width of the base of the box in terms of x, and that the height of the box in terms of x, and then the volume of the box is length times width times height. So once you multiply those three expressions in x together, you get something that has x to the third in it. And then you're going to be asked to find where the maximum, what value of x will give the maximum volume to the box, and what is the maximum volume. So in our pre-calculus course, we're not learning methods for algebraically finding a maximum of a cubic equation with x to the third. So what you have to do is use your graphing calculator. You graph the cubic equation that you create in x. And when you graph it, then you realize that x is only going to be meaningful when your length and width are both 0 or more, or at least more than 0 actually. So your x number cannot be too big so as to make the length or the width be less than 0. So you use those restrictions on x and look at your graph between 0 and the appropriate number, actually between the two places on your graph where the two x-intercepts are. You're going to have this really tall sort of hump in between the two x-intercepts where the graph goes way, way up and comes back down again, hits the x-axis again. And in between there, you want to find the maximum point on that. So you can use your TI-83 or you can use Desmos and find that maximum point on the graph between the two x-intercepts, and that's what you're looking for in that problem. So that maximum point, you're going to find the x value and the y value for it, and you're going to be asked to tell both. To find the x value that maximizes the volume, and that's the x coordinate of that highest point, and the maximum volume is the y coordinate at that same point. Again, it's going to be in between the two x-intercepts of your graph. Okay. And in chapter 4, you should know how to in fact, let me give you a little helpful hint here. I'm looking up something as we speak here in chapter 4. You can expect to see a problem and hear the pages turning as I'm going to refer you to an example in the text, which would be excellent to go by for the kind of problem you're going to see. If you yes, example 5 in your text on page 356 in section 4.4 on solving exponential and logarithmic equations. Look at example 5, solving an exponential equation in quadratic form. Be prepared for a problem, something like that. It's an excellent type of problem. It's actually practical in the real world. Be prepared for a problem like that to solve for x, something like that. Also, be prepared to solve something like example 8 in that same section, solving a logarithmic equation in a different base. So you'll have to know how to use the change of base formula. You'll have to remember the basic principles. For instance, when you get down to either a log equation or an exponential equation and you're stuck and you can do no more algebra, then the recourse we always have to take is to convert that log equation or exponential equation into the other form. So if it's a log equation, you convert it into its corresponding exponential equation. If it's an exponential equation, convert it into its corresponding log equation and proceed from there and get your solution. And finally, you can expect to see a half-life problem having to do with radioactive decay. Give you a little helpful hint here. You should be able to solve a problem something like example 10 on page 332 in section 4.1. And remember the way this works, that for the half-life problem, you actually use a base in an exponential equation, use a base of 1/2, or 0.5 if you prefer. But your base is actually 1/2. And then your half-life goes up into the exponent that's on the base of 1/2 as the denominator of the exponent underneath the variable t. So the exponent on the 1/2 is going to be the variable t divided by the half-life number. So if the half-life is 30 years, your exponent on 1/2 is going to be t over 30. If the half-life is 1,000 years, it would be t over 1,000. And for instance, if you wish to double something, if you're wondering how long would it take something to double, okay, hold on just a moment. No, I'm sorry, I'm getting crossed up with another example I had in mind. If you're wondering like how long it would take for something to turn into a certain percentage of how much was there in the beginning, like how long will it take for, if you have a chunk of this radioactive stuff with a certain half-life, how long will it take till there's only 10% left of the original amount? Well, 10% of the original amount, to make it simple, just let the original amount be 1, since they don't give you a quantity. Just let it be 1. And so 10% of 1, 10% of 1 is just 0.1 or 0.10, however you want to do it. And so that's what you end up with. And if it says how long is it going to take with this particular half-life to end up with that percent of the original amount, if say the half-life was 50 years, to end up with 10%, then you would say your original equation would be something like y equals 1, the original amount, times 1/2 to the t over 50, with a half-life of 50 years. Y equals 1 times 1/2 to the t over 50 power. But we know the y, which is the remaining amount. Y is just 0.1, so 0.1 equals 1 times 1/2 to the t over 50. And then you have an exponential equation that you can convert into a logarithmic equation of base 1/2. I know that sounds funny, but it's not base 10 or e or 2, it's base 1/2. But then you can convert that into a logarithmic equation with base 1/2 and then use your change of base formula, and you can solve the equation and get the answer for how long it would take for an original amount of that stuff with that half-life to end up being only, say, 10% or whatever percent it was of the original amount. And the change of base formula will be on the handout. Change of base formula, definitely. Your basic properties of logarithms and exponents and all that's going to be on the handout. I believe you're going to see the formulas rather than having to memorize all these. I will give you formulas out of all 4 chapters that would be useful to you. So you'll see that with the final exam. So one other thing that covers chapters 1 through 4, the kinds of stuff you can expect to see. In the 3 sections in chapter 8, I'm going to give you a helpful hint. Zero in on the partial fraction decomposition, the second half of section 8.3. Study those 2 techniques in section 8.3 for, I'll even give you the page numbers, example 6 and example 7. in section 8.3. Example 6 is for distinct or different linear factors, and example 7 is for repeated linear factors. And it's a slightly different process with those two systems. So study example 6 and example 7 and expect to see something like that, like one of those two types of problems. So there's a pretty good bird's eye view of what to expect for the exam, and I do want to say I wish everybody the best on this. Please make time, I'm not going to say find time because that can be hard, but make time to study and prepare before your appointment time to take the final. Come prepared as you can be. And 2 hours, I trust, will be plenty of time for everybody. I don't think time's going to be a problem. I certainly hope not. Remember, they'll give you scratch paper, as we call it, if you need it. Bring your calculator, and you can use the computer to use Desmos. And again, I wish everybody the very best on taking the final. And once again, at the end of this, we've been at this about an hour now. Please don't forget this evening, Monday, December 7th, Chapter 4 lab is due. Tomorrow evening, Tuesday, December 8th, the WebAssign online Chapter 4 test is due. And then, of course, the final exam based on your appointments. And you can make appointments anytime from Thursday, the 10th of this week, all the way through Tuesday next week, the 15th. So have a good rest of the day. And again, if anybody has any questions, please let me know. And signing off here.